Okay. There was a question, and I didn't have time to work this out, and I'm not going to, but it concerned the divergence of r over r cubed, an r vector over the cube of its magnitude. And this was mentioned earlier in a previous class, in the first class where we looked at divergence and curl. In terms of the radial vector field, and I commented there that if you divide this radial vector field by its magnitude and then by the square of the distance from the origin to the point xy, you get something that could be a gravitational field. I mean, if you change the sign, have it working inward and so forth. So if you remember that context, this problem, which arose, I think, in some of the homework, is exactly what I was talking about there. Okay, anyhow, you do the divergence of this. Well, your r vector is xi plus yj. Okay, the r vector at the point of the plane is just your xi plus yj vector, and hopefully we're familiar with that. And of course, the cube of the magnitude of that is the cube of the square root of x squared plus y squared. Okay, because the square root of x squared plus y squared is the magnitude of this vector. If we divide the vector by its magnitude, we get a unit vector. And then if we divide by the square of the magnitude, we get a vector that has a magnitude that's inversely proportional to the square of its distance from the origin. And that applies to the field of an electrostatic charge or a gravitational point mass. In any case, now what's the divergence of this? Now you got to work it out. That the divergence, here's your del operator dotted with this vector. Okay, that's a little messy. You know, take the derivative of this. You probably, the x derivative of x over x squared plus y squared to the 3/2, you probably use the quotient rule. You're going to get an x squared plus y squared to the 3/2 plus x times the derivative of that, which will be a 2x times 3/2, which is going to give you 3 times this quantity to the 1/2 and so forth. And that's all straightforward. You do the same thing with y. You could then take the curl of that and you would get 0. First place, this is a radial field. Now I've depicted the field here. It's an inverse square field and it's radial because it's always proportional. It's always in the direction of the r vector, so it's always in the direction away from the origin. And on this circle, assuming this is a circle of uniform radius, a circle centered at the origin, we have some uniform magnitude of the field around this circle. Around a circle that's supposed to be twice as far from the origin, we get vectors 1/4 as long as these. Because if you're twice as far, the magnitude of this vector is half as great. So the inverse, the magnitude of this vector is, if you're twice as far, the magnitude of this vector is proportional to the inverse square of that distance. The inverse square of the factor 2 is 1/4, and you can work that out. In any case, it looks like this. And the curl is easily found to be 0. After you do the divergence, you can do the curl. Again, it's a little messy, but it's not a problem. Just do it carefully, like I don't do things. And of course, the curl being 0, we just reinforce the idea that that's one test for a conservative field. A conservative field being a field that can be derived from a scalar potential. In other words, a field that's the gradient of some scalar function. And this is the gradient of a scalar function. Okay? And the scalar function is just the 1 over r function. Negative 1 over r. Okay, well, there we have that. Here we have this, which pretty much resolves this nightmare.